Guys, I have the pleasure to present you our course entitled Least Squares for Programmers that was prepared by Nicolas Rey, Etienne Cormont, and me, Dmitry Sokolov. We work in a research team named Pixel, and please feel free to contact us if you have any question. In this course, we present how to manipulate geometric objects like curves, images, and surfaces by optimizing their characteristics using least square methods. It is a very efficient tool that doesn't require too much of a mathematical background. The title states for programmers, so please note that we have prepared a GitHub repo that contains source code for all our examples. In addition to that, the course notes contain few optional for reading chapters that I will not present here, but that can be helpful to master the technology. So this course is intended for students or engineers or researchers who know how to program in the traditional way. I mean by breaking down tasks into elementary operations that manipulate combinatorial data structures like trees, graphs, meshes. But here we present you a different paradigm. We describe what is a good result and let numerical optimization find it for us. Anyone able to program computer graphics algorithms can learn how to use least squares with this course. It explains least squares optimization, nowadays a simple and well-mastered technology. We show how this simple method can solve a large number of problems that would be difficult to approach in any other way. So this course provides a simple, understandable, yet powerful tool that most coders can use, and I cannot stress this enough. In the contrast with other algorithms sharing this paradigm, like numerical simulation and deep learning, which are way more complex to master. The importance of linear regression cannot be overstated. The most apparent usage of linear regression is in statistics and data analysis, but linear regression is much more than that. We propose to discover how the same method, least squares, applies to the manipulation of geometric objects. So the first step into the numerical optimization world can be done without strong applied mathematics background. While being simple, this step suffices for many applications and is a good starting point for learning more advanced algorithms. Here we strive to communicate the underlying intuitions through numerous examples of classical problems. We show different choices of variables and the ways the energies are built. Over the last 2 decades, the geometry processing community have used it for computing 2D maps, deformations, geodesic paths, frame fields, etc., etc. Our examples provide many types of applications that can be directly solved by the least square methods. Note that linear regression is an efficient tool that has deep connections to other scientific domains. We will show a few such links to broaden readers' attendees' horizons. So, this course is decomposed in 3 parts. An introduction of least squares, numerous use cases to demonstrate its usefulness, and a presentation of strong relations to adjacent scientific domains. We will start with a gentle introduction of the least squares method, providing some intuitions about linear systems. Then we proceed to the main course. This is about the section 4. How do we instantiate least squares to solve some problems? What can be the choice of variables? How to build an energy? How to deal with constraints? Are we bound by the linearity? And stuff like that. This part, the most interesting part, is the part 4, is thoroughly illustrated with real-world examples and comes with simple source code that is meant to be experimented with. And finally, in the last part, we provide some insights about strong connections between the fundamentals of least squares, probability theory, finite element methods, and neural networks. So, I will start with the probability theory. This is a historical perspective, the origins of the least squares. Let us consider a simple example of coin flipping, also known as Bernoulli's scheme. So, we conduct n experiments, and 2 events can happen in each one, a success or a failure. One happens with probability p, the other one happens with probability 1 minus p. Our goal is to find the probability of getting exactly k successes in these n experiments. This probability is given by the Bernoulli's formula. If we take an ordinary coin, it means that p is equal to 0.5, flip it 10 times, n equal to 10, and we count how many times we get the tails. Thus, if we have fixed the probability of successes, 1/2, and also fixed the number of experiments, 10, then the possible number of successes can be any integer between 0 and 10, but these outcomes are not equiprobable. It is clear that 5 successes are much more likely to happen here. For example, the probability of encountering 7 tails is about 12%. If we have a biased coin with, say, probability 0.7, then the probability of having 7 successes is about 27%. Now, let us look at the same problem from a different angle. Suppose that we have a real coin, like this one, but we do not know its distribution of a priori probability of success / failure. However, we can toss it 10 times and count the number of successes. For example, we have counted 7 tails. Would it help us to evaluate p? We can try to fix n equal to 10 and k equal to 7 in Bernoulli's formula, leaving p as a free parameter. Please note that to ease visual parsing of the formulas, throughout all the presentation I highlight known values in green and unknown values in red. So now Bernoulli's formula can be interpreted as the plausibility of the parameter p being evaluated. I have even changed the function notation. Now it's denoted as L, like likelihood. That is being said, the likelihood is the probability to generate the observation data. In our experiment, it's 7 tails out of 10 experiments. So, for the given it's the probability to generate the observation data for the given value of the parameter. For example, the likelihood of a balanced coin with p equal to 1/2 with 7 tails out of 10 tosses is approximately 12%. Here is a plot of the likelihood function for the observation data with 7 tails out of 10 experiments. As I said, please note that this is a continuous graph because here is P and here is the likelihood. So if we have 7 tails out of 10 experiments, the probability to have a balanced coin is about 12%. And the most probable explanation for this experiment normally is to have probability 0.7. Okay, let us move on. So having a model, we are looking, having a model or having an experiment, we are looking for the parameter value that maximizes the likelihood of producing the observation we have. In our particular case, we have a function of one variable, and we are looking for its maximum. In order to make things easier, I will not search for the maximum of L, but for the maximum of logarithm of L. The logarithm function is strictly increasing, so maximizing both is the same thing. The logarithm has a nice property of breaking down products into sums that are much more convenient to differentiate. So we are looking for the maximum of this function. This is why we will equate its derivative to 0. The derivative of logarithm p is 1 over p, so the equation is really easy to solve. As we have solved from the plot, the maximum likelihood, about 27%, is reached at the point p equal 0.7. Well, duh. Just in case, let us check the second derivative. In the point p equals 0.7, it's negative. Therefore, the point is indeed a maximum of the function L. The point of this exercise is to gently introduce a method of maximum likelihood estimation. The idea to estimate parameters of a probability distribution by maximizing a likelihood function, so under the assumed statistical model, the observed data is the most probable. If the likelihood function is differentiable, the derivative test for the determining maxima can be applied. In some cases, like in one we have just saw, the first order conditions of the likelihood function can be solved explicitly. As we will see shortly, ordinary least squares estimator maximizes the likelihood of the linear regression. Okay, let us consider a second example. Let us imagine that we have a constant physical quantity that we want to measure. For example, it can be a length to measure with a ruler or a voltage to measure with a voltmeter. In the real world, any measurement gives only an approximation of this value, but not the value itself. The methods I'm describing here were developed by Gauss at the end of the 18th century when he measured the orbits of celestial bodies. For example, if we have a battery, we can measure its voltage n times, and obviously we will get n different measurements. Which one should we take? Well, all of them. So let us say that we have n measurements ui. Let us suppose that each measurement ui is equal to the real value plus a Gaussian noise. The noise is characterized by two parameters: the center of the Gaussian bell and its width. In this case, the probability density can be expressed as an exponent function. So, our goal is to estimate the unknown parameters that are shown in red. So having n measurements ui, our goal is to find u and sigma that maximize the likelihood. The likelihood, I have already applied the logarithm, can be written as follows, and here we use our assumption that the measurements are independent and identically distributed, so we have a product here. Then let us rewrite the expression. The product goes outside as a sum. Then this product can be expanded as a sum of these two terms. And the last one, this is equal to this expression. Please note that this part does not depend on the measurements we made. So to find the maximum likelihood, it is the same thing as to find the minimum of this function. So we can conclude that under Gaussian noise, maximization of the likelihood is equivalent to least squares minimization. This is a very important step. And then everything is strictly as it used to be. We equate the partial derivative to 0, and it is easy to see that the most plausible estimation of the value u is a simple average of all the measurements. Finally, the most plausible estimation of sigma turns out to be the standard deviation. Well, such a convoluted way to obtain a simple average of all measurements. In my humble opinion, the result is worth the effort. By the way, averaging multiple measurements of a constant value in order to increase the accuracy of measurements is a quite standard practice. For example, ADC averaging, so when we do an analog to digital conversion. Note that the hypothesis of the Gaussian noise is not necessary in this case, it's enough to have an unbiased noise. While we have seen that for measuring a constant value, it suffices to take a simple average to get the most plausible explanation, it is much harder for less trivial cases. Let us consider the last example, and here we are talking about ordinary least squares. Say we want to calibrate a spring scale with the help of a reference weight. What a spring scale is, so we have a spring, we put some weight here, and we measure the length of the spring. Suppose that we have n reference weights of mass xj. We weigh them with a scale and measure the length of the spring. So we have n spring lengths yj. Hooke's law tells us that the spring stretches linearly on the force applied. This force includes the reference weight and the weight of the spring itself. Let us denote the spring stiffness as A. The spring length stretched under its own weight as B. Then we can express the plausibility of our measurements still under the Gaussian measurement noise hypothesis in the following way. So it's a logarithm, our measurements are identically and distributed and independent, so we have a product here, and under applying the logarithm function, this product expands into a sum of simpler functions. This part does not depend on the measurements, so we are not interested in this part when estimating the maximum likelihood function. So it's easy to see that only this part matters, and maximizing the likelihood L is equivalent to minimizing the sum of squared estimation error. Thus, we are looking for the minimum of the function s defined as follows. As before, the known values are shown in green and unknown values are shown in red. The image on the right illustrates the formula. We are looking for such a straight line that minimizes the sum of squared lengths of green segments. And then the derivation is quite straightforward. We equate the partial derivative to 0, and we obtain a system of two linear equations with two unknowns, and we can use any method to get the solution. And here we can see that the solution is much less trivial than the previous example. It is not a simple average between all the measurements. Okay, the idea behind all this section was to give some historical perspective. The least squares method is a particular case of maximizing likelihood in cases where the probability density is Gaussian. If the density is not Gaussian, the least squares approach can produce an estimate different from MLE, maximum likelihood estimation. By the way, Gauss himself erroneously conjectured that the type of the noise is of no importance and the only thing that matters is the independence of trials. As you have already noticed, the more parameters we have, the more cumbersome the analytical solution become. Fortunately, we are not living in 18th century anymore, we have computers. Next, we will try to build a geometric intuition on least squares and see how least square problems can be efficiently implemented. Okay, we are going to the second section of our presentation. As you have probably noticed, I have promised you for programmers in the course title, and we have not seen a single line of code yet. It's time to change that. In the last example, we had to solve a 2x2 linear system, so before attacking larger least squares with an aid of a computer, we need to recall how to solve systems of linear equations, and to do so, we will write our first program right now. Let us examine the following Python program. We start from a 16 elements array, and we iterate over and over a simple procedure. We replace each element with an average of its neighbors. The first and the last elements are fixed. So basically, at each iteration, we create a new list by copying the first element, by copying the last element, and for the interior, the element xi is replaced by an average of xi minus 1 plus xi plus 1. Here's a quick test. What should we get in the end? Does it converge or does it oscillate infinitely? Take a few seconds. Well, intuitively, the first element is fixed, the last element is fixed, and then, for example, this element will move here in the middle of its neighbors. So, intuitively, each peak in the array is cut out, and therefore the array will be smoothed over time. Here is the evolution of the data over time. So this is initialization. At the first iteration, we get a smoother version, and then it smooths and it smooths until we obtain a straight line. But is there a way to predict the result without guessing it and without executing the program? The answer is yes, and let us put the program aside for a moment and recall how to solve systems of linear equation with a computer. Let us suppose that we have an ordinary system of linear equations. As before, the known values are highlighted in green and unknown values are highlighted in red. So we have a matrix equation AX equal B. It can be rewritten, this system, it can be rewritten by leaving xi at the left side of the equation. So basically we take x1, we get it outside of the equation, and all the rest goes to the right side of the equation. So this system can be rewritten in this way. Now, let us start with an arbitrary vector x0 that approximates the solution. For example, it can be any vector, for example, a zero vector. Then, if we plug this vector in the right side of the equation, we can compute an updated approximation x1. So we took this vector and we plugged it in the right-hand side of the equation, and we obtained an update for the approximation. Thus, we can build a sequence of approximations, and under some assumptions of the system, this procedure converges to the true solution. Well, for example, we cannot have zeros on the main diagonal. This iteration is known as the Jacobi method. Of course, there are other much more powerful numerical methods, but this is the simplest one. So, repeating the process k times, the solution can be approximated by the vector xk, and it converges to the solution. What is the connection to our Python program? So this is the same program that we saw before. In fact, we replace each interior node xi with the average of its values, and this can be rewritten as follows. It turns out that our program solves the following system with the Jacobi method. Since you can pause the video, do not take my word for it, grab a pencil and verify it. So, if we consider the array as a sampled function, the linear system here prescribes a constant derivative. So we have a first-order finite difference equal to another first-order finite difference that propagates. And so we want to compute a function with a constant derivative with two fixed extremities. Therefore, the result can only be a straight line. There is a very interesting modification of the Jacobi method named after Johann Carl Friedrich Gauss and Philipp Ludwig von Seidel. This modification is even easier to implement than the Jacobi method, and it often requires fewer iterations to produce the same degree of accuracy. With the Jacobi method, the values obtained in the kth approximation remain unchanged until the entire kth plus 1 approximation has been calculated. With Gauss-Seidel method, so we have x0 here, and we need to have all x0s until we compute a copy x1. With Gauss-Seidel method, on the other hand, we can use the new values that we have just calculated as soon as they are known. So the first equation can be computed just as with the Jacobi method, but for the second one, we can reuse x1 instead of x0. So with the Gauss-Seidel method, we can write the same program by performing in-place calculations. The recursive formulas can be written as follows. So for the Jacobi method, all the approximation xk can be computed from the approximation xk minus 1. And with Gauss-Seidel method, to compute an approximation xk, we use the approximation x time xk minus 1 and the approximation at the time xk where it is available. It allows us to perform all the computations in place. So basically, back to our program. This is the program we have already saw that can be rewritten in a simpler manner. And the second program solves exactly the same system of equations, but with a Gauss-Seidel method. Okay, so here is an evolution of the data over time, and we can see that with the Gauss-Seidel method, we obtain the same straight line segment, but it converges quickly. Here it took about 50 iterations, and for the Jacobi iterations, we had to make about 500, if I'm not mistaken. Okay, let us go beyond the 1D example. And now I propose to see that exactly the same approach works well also for 3D surfaces. So, what have we done here? We have computed a function whose first derivative is constant and it has prescribed boundary conditions. We can see exactly the same thing from a different perspective. We can put this to the left side, and then we can rewrite the same system as follows, and we can see that this part corresponds to a second order finite difference that must be 0. So we can say that our program computes a function with prescribed boundary and with 0 second derivative, and naturally it corresponds to a straight line segment. Well, if we move to a 3D example, we want to compute a surface with prescribed boundary, and we want to find the geometry of the interior. For example, imagine that we have a very simple surface that is made of 3 triangles, vertex 1, vertex 2, vertex 3, and the interior vertex 4. The vertices 1, 2, and 3 are fixed, and the 4th vertex is free to move, and we want to find its final position. The code that you see here does exactly this thing. It differs a bit from what we saw for 1D, because if we write the code in the same way, it will be unbearably slow, and so this is a Pythonic way to do such things. So still, we want to solve the Laplace's equation delta f equal to 0 with Dirichlet boundary conditions. So just as before, 0 second derivative with fixed boundary. And we perform a number of Gauss-Seidel iterations to obtain the geometry for the interior vertices. However, why does the code not look like the previous one? In fact, it's simply a speed up, a Pythonic way to write the code, and we will just see how it works. So I build here, so I read a mesh from a file. Here, I read a mesh from a file, and for example, our mesh looks like the 3 triangles that I have just drawn. And then I build a matrix. In this case, it will be 4 by 4 matrix. What do we have in this 4 by 4 matrix? So basically, it is filled with zeros in the beginning, and then for each vertex v, for each iterate through all the rows of our matrix. We will have a 4 by 4 matrix, and then if the vertex v is a boundary vertex, we will assign a 1 to the diagonal of this 4 by 4 matrix. So basically, the vertex 1 is a boundary vertex. The first row will be 1 and 3, 0. The second vertex is a boundary vertex, so it will look like this one. And the third row will look like this one. Then the fourth vertex is not a boundary vertex, so we will put 1/3 here, 1/3, 1/3, 1/3, and 0 here. Okay, this is our matrix A. And then in our Gauss-Seidel iterations, I multiply the geometry of the vertices by this matrix to obtain a new approximation. So if we have x1, y1, z1, x2, y2, z2, z2, x3, y3, z3, x4, y4, z4. If we multiply these vertices, then we will obtain an updated approximation of the geometry of our surface. Well, naturally, we will just copy x1, y1, z1, x2, y2, z2, x3, y3, z3, and then for the fourth vertex, the interior vertex will be placed at the very center of its neighbors. So it will be x1 plus x2 plus x3 divided by 3, and the same for the y and z coordinates. So I have built a matrix. And in our code, I simply update a number of times the geometry of our surface by multiplying the geometry by this matrix. So this is a good way to smooth a surface because this multiplication, it is not internally done in Python. Python calls some code that is written in Fortran or in C++, I don't really know. Okay, if we execute this code on a less trivial surface, that is what we obtain. So here is my face digitized because I don't want to mutilate other people. And if we take this surface's input, after a few iterations, it becomes smoother, and after a number of iterations, it converges to a minimal surface. The result is the minimal surface respecting the boundary conditions. In other words, imagine that we make a loop from a rigid wire, we soak it in a liquid soap, and then the soap film on this loop is the solution for our equation, Laplace's equation, delta f equal to 0 with prescribed boundary. Okay, we are moving on to the last example in this section. We have just saw how to solve the Laplace's equation. So basically, we have solved 2 times for 1D example and for 3D surface the equation delta f equal to 0. So we looked for a function f with 0 second derivative. And if we fix the boundary, then naturally the solution is a straight line segment. So here I propose to modify a little bit the equation, the program. So basically we add a small term to the right-hand side of our equation. Take a few seconds. Think and tell me what is the result of this program. Well, it is easy to see that for an interior node xi, we are trying to solve the equation minus xi minus 1 plus 2xi minus xi plus 1 equal some function of I. And this function g is a linear function. So we are looking for a function whose second derivative, because this is a second order finite difference, we are looking for a function whose second derivative is a linear function. Therefore, the solution must be a cubic polynomial. So here is evolution of the data over time, and the ground truth polynomial, the cubic polynomial, is shown in green. Congratulations, you have just solved a Poisson's equation, so equation of type delta f equal to g. The Laplaces and the Poisson's equations are the most used equations in computer graphics. We will meet it quite a few times later in this course. So, the takeaway message here. We just saw that mere 3 lines of code can be sufficient to solve a linear system, and thus effectively solving even a differential equation. While it's extremely cool, it raises many questions. First, what are the practical consequences for a programmer? How do we build these systems, and where do we use them? Refer to the course notes for an optional chapter on finite element methods that elaborates a little bit around the code that we have just saw. But since our main goal is the least squares method, we will see how to minimize quadratic functions and how solving linear systems can be useful to a minimization of quadratic functions. Recall that the main goal is to study least squares. Therefore, our main tool will be the minimization of quadratic functions. However, before we start using this power tool, we need to find where its on-off button is located. First of all, we need to recall what a matrix is. Then we will revisit the definition of positive numbers, and only then we will attack minimization of quadratic functions. In this section, matrices will be omnipresent, so let us recall what it is. Pause the video for a few seconds and try to formulate what the matrix is. The answer is very simple. A matrix is just a locker that stores stuff. Each piece of stuff lies in its own cell. Cells are grouped in rows and columns. In our particular case, we store real numbers. For a programmer, an easiest way to imagine a matrix A is something like float A M. Why would we need a storage like this? What does it describe? Maybe I will upset you, but a matrix by itself doesn't describe anything at all. It just stores stuff. For example, you can store quotients of a function in it. Let us put aside matrices for a second and imagine that we have just a number a. What does it mean? Who knows what it means? For example, it can be a quotient inside a function that takes one number as an input and gives another number as an input. One possible instance of such a function a mathematician could write down as f of x, y of x equal to a times x. In the programmer's world, it would look something like this. On the other hand, why this function and not another one? Let us take another one. Y of x equal to a times x squared. And the programmer would write it like this. One of these functions is linear and the other one is quadratic. Which one is correct? Neither one. A number a doesn't define it. It just stores a value. Build the function you need. The same goes for matrices. They give storage space when simple numbers, scalars, do not suffice. A matrix is a sort of a hypernumber. The addition and multiplication operations are defined over matrices just as over numbers. Let us suppose that we have a 2 by 2 matrix A. The matrix doesn't mean anything by itself. For example, it can be interpreted like a linear function. Here goes the programmer's view on the function. This function maps a two-dimensional vector to a two-dimensional vector. Graphically, it's convenient to imagine it as an image transformation. We give an input image, and the output it is the stretched and or rotated, maybe even mirrored version of the image. On the other hand, nothing prevents to interpret the matrix A as a quadratic function that maps a vector to a scalar. Note that the square is not well defined for the vectors, so I cannot simply write x squared as I wrote in the case of ordinary numbers. For those who are not at ease with matrix multiplications, I highly recommend to revisit it right now and check, for example, that the expression x transposed ax produces a scalar value. To this end, we can explicitly put brackets around the left part. Recall that in this particular example, x is a two-dimensional vector, and we store it in a 2 by 1 matrix. So this is a 2 by 1 matrix, this is a 1 by 2 matrix, and this is a 2 by 2 matrix. Then this product here will be a 1 by 2 matrix, and the final product here is a 1 by 1 matrix, or in other words, a scalar. Returning to the cozy world of programmers, we can write the same quadratic function as shown in the bottom of the slide. And graphically, we can interpret it like a paraboloid surface. So we have two input vectors, x0 and x1, and the surface produces the scalar value for a given value of x0 and x1. Allow me to ask you a very stupid question. What is a positive number? We have a great tool called the predicate greater than. Do not be in a hurry to answer that a number a is positive if and only if a is superior to 0. It would be too easy. Let us define the positivity as follows. The real number a is positive if and only if, for all non-zero real x, the condition a times x squared is satisfied. This definition might look pretty awkward, but in fact it applies perfectly to matrices. So, we can extend the definition of positivity to matrices. Let us say that a square matrix A is called positive definite if for any non-zero x, the condition x transpose times A times x is superior to 0. In other words, the corresponding quadratic form is strictly positive everywhere except at the origin. What do we need the positivity for? As we have already mentioned, our main tool will be the minimization of quadratic functions. In fact, it would be nice to be sure that the minimum exists. For example, the function f of x equal to minus x squared has no minimum because the number minus 1 is not positive. Both branches of the parabola f of x look down. Positive definite matrices guarantee that the corresponding quadratic form forms a paraboloid with a unique minimum. Here is an illustration. I took 7 different 2x2 matrices and I provide an interpretation for each one of them as a linear function from a plane to a plane, as well as the corresponding quadratic forms. So, for example, let us consider the identity matrix, the simplest one. And if we interpret this matrix as a linear function, we have a function that takes a 2D point as the input and that returns a 2D point. By applying this function to all points in the plane, we obtain a transformation of the plane, and we can visualize it by transforming, for example, an image. So this is an identity transformation. It will leave the image unchanged. So here you can see the reference image that I took, the image of Bubble Bobble. If we modify this quotient, for example, it corresponds to a transformation that compresses the image along the axis x. And then we can have other transformations like a mirror or rotation or shear and other ones. Okay. Still with the identity matrix, how do we interpret it as a quadratic function? Well, this is really simple. It suffices to multiply xy times 0, 1, 1, the identity matrix xy. This is equal to x squared plus y squared. So here you can see the plot of the function x squared plus y squared, and it forms a nice round paraboloid. In the previous slide, we were talking about the positivity of numbers and matrices, and among 7 matrices that I listed here, 4 are positive definite. What does it mean? What does it mean graphically? It means that the corresponding quadratic forms are the paraboloids, that looks towards the top, and these functions have unique minimum in each case. So there is a minimum here, 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 and here. This matrix, for example, is not positive definite, and it turns out that it is a negative definite matrix, so it forms a paraboloid that looks towards the bottom, and it has a unique maximum. There are other matrices like this one that are not positive definite nor negative definite. So this is indefinite matrix, and the corresponding quadratic function forms a saddle shape. A very interesting thing to note here is that when people are talking about a positive definite matrix, very often they imply the symmetry of the corresponding matrix. So I have listed 5 symmetric matrices here and 2 asymmetric matrices. What does it mean for a matrix to be symmetric? it means that it is equal to its transpose, and in the 2D case, that, for example, the anti-diagonal elements must be equal. This is the case for 5 matrices here, and for example, this matrix is not symmetric because the anti-diagonal elements are not equal. So why do people imply symmetry when they are talking about positive definiteness? It's simply because it eases some things, because for any quadratic function, for any quadratic form, we can find a symmetric matrix that represents it. For example, if we take a quadratic form x squared plus xy plus y squared, it can be represented as a quadratic form xy times 1, 1, 0, 1 times xy, as shown here. So we take the quadratic form and we represent it by an asymmetric matrix. But in fact, this is exactly the same function. So this matrix, that is a symmetric matrix, represents the same quadratic form, and it can be easily verified that xy times 1, 1/2, 1/2, 1 times xy is equal to x squared plus xy plus y squared. So, once again, for any quadratic form, it is possible to represent it by a symmetric matrix, and so for quite often it's very handy, and when we are talking about positive definite matrices, most often that implies symmetry. Let us return for a while to the unidimensional world. I want to find the minimum of the function f of x, defined as ax squared minus 2bx, with number a being positive. Since the number a is positive, therefore the minimum exists, and to find it, we equate the corresponding derivative with 0. It is really easy to differentiate a unidimensional quadratic function, so our problem boils down to the equation ax minus b equal to 0, and with some effort we can find the solution b divided by a. This figure illustrates the equivalence of two problems. The solution of the equation ax minus b equal to 0, so this point, coincides with the minimizer of the quadratic function ax squared minus 2bx. My point is that our main goal is to minimize quadratic functions. We are talking about least squares here. And since the only thing that the humanity knows to do well is to solve linear equations, it's really great that one is equivalent to the other. The last thing to check is to be sure that we have this equivalence in the multivariate case, and to do so, first we will prove 3 theorems. The first theorem states that a 1-by-1 matrix is invariant with respect to the transposition. Well, this is a very hard theorem, and I will leave the proof as an exercise. The second theorem says that gradient of b transposed x is equal to the gradient of x transposed b is equal to b. So we know how to differentiate a univariable function. We know that if we want to differentiate bx with respect to x, the result is simply b. And our theorem extends this definition just to a multivariate case. No surprises here. The derivative of bx is equal to b, and the gradient of b transposed x is equal to b. It's the same result, just in a matrix notation. The proof is really straightforward. It suffices to write down the definition of the gradient. So the gradient of a scalar function b transposed x is a vector of partial derivative with respect to each coordinate. Then, for example, for the first coordinate, we write down what means b transposed x, and it's a simple sum bi times xi. And since there is only one term that depends on x1, it's b1, so we give the first coordinate of our result, and the same goes for the same coordinates up for all the coordinates, so the gradient of b transposed x is equal to b. Now, by applying the first theorem, this scalar is equal to this scalar, so we get also the second equation. Now let us switch to quadratic forms. We know that in the case of a real variable, of a real function of one variable, we have the derivative of ax squared is equal to ax. But what about quadratic forms? So here comes the third theorem that tells us that the gradient of the quadratic function, a quadratic form x transposed ax, is equal to a plus a transposed times x. And note, if the matrix A is symmetric, then the gradient of the quadratic form is equal to 2ax, and you can see the perfect correspondence between the univariate and the multivariate cases. The proof of this theorem is really straightforward. It suffices to express the quadratic form as a double sum. So here I write down simply the definition of the matrix multiplication. And then this double sum, let us differentiate our quadratic form with respect to the variable xi. So I take the double sum and I differentiate it with respect to xi. I can split the sum, the double sum, into 4 cases, whether k1 and k2 are equal or not to the I, and I remind you that we are differentiation with respect to xi. So we have a double sum where both indices are not equal to I, where only the second index is not equal to I, where the first index is not equal to I, and both indices equal to I. And then it's really simple to differentiate our expression. So this sum goes out because no terms, no variables, xi doesn't appear in this sum, and the 3 other sums are really easy to differentiate. And finally, we can regroup. We can put one of these terms in one sum, the other term in the other sum, and we obtain the following expression that can be also rewritten as a sum of aij plus aji times j. So it's basically the definition of A plus A transpose times X. Okay, finally, we have all the tools necessary to minimize multivariate quadratic functions. Recall that for the univariate case, for a real number A superior to 0, Solving the equation ax equal to b is exactly the same thing as to minimize the quadratic function ax squared minus 2bx. Well, the same thing happens in the multivariate case. If we want to minimize the quadratic form x transposed ax minus 2b transposed x with a symmetric positive definite matrix A, recall that we need the matrix to be positive definite as we have needed the quotient A to be superior to 0. We can equate the derivative of the quadratic form to 0. Then the gradient is a linear operator, so we can split it into a sum of two terms, and we can apply to our differentiation theorems that we have just proven. So the gradient of x transposed ax is equal to this expression, and the gradient of b transposed x is simply equal to b. Now recall that A is a symmetric matrix, so this expression is equal to 2A, and we can get rid of the quotient 2. To recapitulate, to solve the linear system ax equal to b with a symmetric positive definite matrix A, it is exactly the same thing as to minimize the corresponding quadratic form. Now we can move on to the main content of our course. Imagine that we have 2 points on a plane x1, y1 and x2, y2. And we want to find an equation for the line passing through these 2 points. The equation of the line can be written as y equal to alpha x plus b. That is, our task is to find the quotients alpha and beta. As before, I highlight known values in green and unknown values in red. So this is a secondary school task, and let us write down the corresponding system of equations. So we have 2 equations with 2 unknowns, alpha and beta, and the rest is known. In general, there exists a unique solution. We can rewrite it in a matrix form. So we have a matrix equation ax equal to b, and we can find the solution by inverting the matrix A. Well, this is nice, but what happens if we add a third point? So if we add a third point x3, y3, we obtain a system of 3 equations, and in a matrix form it will have the following shape, and the matrix A is rectangular and thus not invertible. Well, sounds legit. We have only 2 variables and 3 equations, and in general such a system has no solutions. This is a perfectly normal situation in the real world, where the data comes from noisy measurements, and we need to find parameters alpha and beta that fit the measurements the best. We have already encountered this situation in the very beginning of the course, when we have calibrated a sprint scale. However, back then the solution we have obtained was purely algebraic and quite cumbersome. Let us try a more intuitive way. Our system, this one, can be rewritten as follows. Or in a shorter form, we are looking for 2 scalar values a and b, such that the linear combination, we're looking for 2 scalars alpha and beta, such that the linear combination alpha I plus beta j is equal to the known vector b. The vectors I, j, and b are known, they are highlighted in green. And the linear combination alpha I plus beta J generates a plane. If the vector B does not lie in this plane, there is no exact solution. However, we are looking for approximate values. Let us denote the solution error for a given pair of parameters alpha and beta. We have the solution error that we call E function of alpha and beta. Our goal is to find the values of the parameters alpha and beta that minimize the norm of the error vector. Okay, the norm of the error vector is minimized, obviously minimized, when the error vector is orthogonal to the plane generated by the basis ij. So we can write it as a system of two equations. Orthogonality of the vectors means the zero dot product. So I is orthogonal to E and J is orthogonal to E. We can expand this expression. So this is the vector E, this is a vector I, and this is a vector J. And it must be orthogonal because the corresponding dot products are zero. It is a very interesting thing here. We can rewrite once again this expression in the following form. In fact, if we denote this matrix as A transposed, then we have a matrix equation A transposed times AX minus B equal to the zero vector. And the amazing thing here that in a general case, the matrix A transposed A can be invertible. So the matrix A is a rectangular matrix, but the product A transposed A is square. In our case, our matrix A is a 3 by 2 matrix. So A is a 3 by 2 matrix. So A transposed A is a 2 by 2 matrix. So to minimize the norm of the error, we can simply solve the following linear system of equations. Okay, please note that the matrix A transposed A is a pretty remarkable. First of all, A transposed A is a symmetric matrix. And this is really easy to show. It suffices to write a transposition of the matrix. So we can distribute the transposition. So it is equal to the right matrix transposed times the left matrix transposed. And then it's equal to A transposed A, and this is the definition of a symmetric matrix. But then, even more important, is that A transposed A is a positive semi-definite matrix. It means that this quadratic form is never negative. It's really easy to see. It suffices to note that this quadratic form can be written in as AX transposed times AX, and it's a dot product of the vector AX with itself, and obviously cannot be negative. Moreover, when the matrix A has a full rank, then the matrix A transposed A is a positive definite. Well, we have just saw how to minimize a quadratic form in 2 dimensions in in an arbitrary number of dimensions, the same reasoning applies, and here is an algebraic way to show it. So ax minus b is the residual vector, the error vector that we want to minimize. So we minimize the square of its norm. We can rewrite as follows. We want to minimize the dot product of the vector ax minus b with itself. Then we can distribute the transposition, make it enter the parenthesis a, and rewrite in the following way. Then we can multiply all things out, open the parenthesis, and we obtain the following expression. And note that we have a term b transposed b here that is constant and does not depend on x. So it doesn't play any role in the minimization here. It simply translates the quadratic paraboloid and plays no role, so we can get rid of it and say that this minimization is equal to this one. And here we use the fact that this is a scalar, this is a scalar, and those are the same things. We have used the first theorem that we have proven 5 minutes ago. Okay, and finally, we can call this matrix as A prime and this matrix as B prime. And then the takeaway message here is that the least squares problem ax minus b to minimize ax minus b squared is exactly the same thing as minimizing the quadratic function x transposed a prime x minus 2b prime transposed x with, in general, a symmetric positive definite matrix A prime. And this can be done by solving a linear system A prime x equal to B prime. Okay, enough with the theory. I'm eager to write some code. After all, I have promised for programmers in the title of the course. So this section is the main part of the course. The main programs will be here, and we will consider few different problems that can be solved with the least squares. The idea is to show main turning knobs to allow you to instantiate the least squares in different settings for your problems. Let us start with a tiny example from the optimal control theory. Optimal control deals with the problem of finding a control law for a given system such that a certain optimality criterion is achieved. Well, this phrase is way unspecific. Let us illustrate it. Imagine that we have a car that advances with some speed, say 0.5 meters per second. The goal is to accelerate and reach, say, 2.3 meters per second. Here I sample the signals every 1 second and I leave a half a minute to reach the given speed. Note that we cannot control the speed directly, but we can act on the acceleration via the gas pedal, and we can model the system with a very simple equation that tells us that the speed at time I is equal to the initial speed v0 plus the integral of the acceleration. Recall that I highlight unknown values in red and known values in green. So our goal is to find a sequence of u that optimizes some quality criterion j that depends on the state of the system and the control u. The case where the system dynamics is described by a set of linear differential equations and the cost j is described by a quadratic functional is called a linear quadratic problem. Let us test few different quality criteria for the same problem. For example, What happens if we ask for the car to reach the final speed as quickly as possible? It can be written as follows. We penalize the deviation of the velocity vi from the goal vn. And here I have just expanded the definition of the expression of vi. To minimize this criterion, we can solve the following system in the least square sense. In particular, in this particular case, the system is not overdetermined, so it's really easy to see that we have the solution u0 equal to vn minus v0, and the rest of the ui is equal to 0. This obviously results in a quite brutal acceleration, well beyond of physical capabilities of our car. So, how to cope with the problem? Let us try another criterion that penalizes large accelerations. Here we say that at every moment we want the acceleration to be as low as possible by taking a sum of ui squared. And in addition to that, I put a constraint to the system that forces the car to reach the goal speed after half a minute. This sum is the final speed for the car, and I want it to be close to Vn in the end. Here is a piece of Python code that solves the system. So we start by building a system matrix A. So this is the matrix A multiplied by the unknowns u. So the matrix A is a stack of an identity matrix. Here we have an identity matrix with a last row filled by ones. Here and here. The vector B, the right-hand side, is the zero vector stacked with one value Vn minus V0. We obtain the control signal U by solving the system A transposed A U equal to A transposed B. And in the final, we reconstruct the velocities from the control signal that we have just computed. Here is a plot of the solution. Indeed, the acceleration is really low. However, the transient time becomes unacceptable. We cannot leave the car 30 seconds to accelerate to 2.3 meters per second. Well, minimization of the transient time, the first example, and low acceleration, the second example, are competing goals, but we can try to find a trade-off by mixing these goals. So let us try a third criterion that asks to reach the goal as quickly as possible while penalizing large accelerations. So I want to reach the goal as quickly as possible, and I want the accelerations to be slow at every moment, accelerations to be low at every moment. Note the quotient. So this can be solved by solving this linear system in the least square sense, and note the quotient 2 or 4 when squared, and recall that by changing this quotient we can attach more importance to one of the competing goals. So following listing solves this system, and again here is the matrix A times U, and we build the matrix A by from a stack of a lower triangular matrix of ones, and a diagonal matrix built with 2 at the diagonal. And the right hand side is the vector Vn minus V0 stacked with the 0 vector. And once again, we are solving the system A transposed AU equal to A transposed B in this line, and we recompute the velocities from the control signal we have just computed. Here is the plot of the solution, and it looks like a reasonable behavior for a car. In practice, just like we did in this section, engineers try different combinations of competing goals until they obtain a satisfactory transit time while not exceeding regulation capabilities. So the takeaway message here is that for the same problem, the same choice of the variables, tweaking the objective function produces very, very different results. Use it to your advantage. Now let us move way closer to computer graphics. We will be talking here about Poisson's equation that is widely used, for example, in image editing and geometry processing. We will see that shortly. But first, let us start with the 1D basics. So the problem is to find an unknown function f of x defined over some interval that resembles an input function g subject to boundary constraints over f. Recall that I highlight unknown values in red and known values in green. We can formulate this problem as find f whose second derivative is equal to the second derivative of g with boundary of f fixed. The easiest way to solve the problem is to use a Neanderthal smoothing method that was very common a couple of decades ago. For example, we can sample the function with 33 samples. We can pre-compute the samples for the function g, and then I initialize the function f as the boundary values plus the 0 function for the interior of the interval. And then I smooth the function f just as we have done a number of times before by Gauss-Seidel iterations. So I perform a number of Gauss-Seidel iterations. And then inside these Gauss-Seidel iterations, I prescribe the second order finite differences over f to be equal to the second order finite differences over g. This approach is very simple to implement, however, it is quite hard to tweak. Let us consider the same thing from a different perspective. I want to reformulate the problem as a minimization. Note that solving Laplace's equation delta f equal to 0 subject to appropriate boundary conditions, is equivalent to solving the variational problem of finding a function f that satisfies the boundary conditions and has a minimal Dirichlet energy. So it's the same as argmin in f integral gradient of f squared. Indeed, application of Euler-Lagrange equations for the minimization problem results in the Laplace's equation. Same goes for Poisson's equation. Solving for delta f equal to g is equivalent to minimizing the integral of the squared norm of gradient f minus gradient g. Turns out it's a quadratic energy to minimize, and we know just a method to do this efficiently. Thus, after discretization, we need to solve the following system in the least square sense. Here I simply want first order finite differences over f to be equal to the first order finite differences over g. Here is a short Python code that just solves the system. As before, we have 33 samples, then I pre-compute the function g, And then we fill the matrix A. So this is the matrix A times unknowns F. The matrix A is filled with two diagonals built from ones and minus ones. So I initialize the matrix A as a zero matrix, and then I fill two diagonals with ones and minus ones. And then I compute the right-hand side vector B. And so I'm solving the system AF equal to B. In the least square sense, so basically I'm solving the system A transposed A, F equal to A transposed B. And we get the solution we have solved before, a nice smooth function F. Okay, now we are ready for a simple image editing example. I want to replace the baseball from the left image with the football in the middle image. Obviously, a direct overlay leads to a non-satisfactory result, as we can see in the right image. How to swap the content seamlessly? Poisson's equation can be of help here. We can do better. So we will solve a one linear system per color channel. So all color channels are solved independently. And we can say that we manipulate grayscale images. Let us say that we have two real-valued functions. A, the sub-image of the baseball photo, for example, for the red channel, and B, the football image, defined over a domain omega. Here, for the sake of simplicity, we consider a rectangular domain omega. So, we are looking for the function f that takes its boundary conditions from A, and it takes the gradient from B. We can discretize the problem exactly as in the previous example. We have W by H pixels grayscale images A and B, and to compute a W by H pixels image F, we can solve the following system in the least square sense. Note that if we solve for an image that is 1000 pixels wide and 1000 pixels tall, we have 1 million unknowns, and thus the matrix A transposed times A is 1 million by 1 million. Fortunately, the matrix is sparse. It means that it contains only few non-zero entries at each row, so the problem is still tractable. As usual, you can find the source code in the GitHub repository, and I will show you it shortly. And here is the result. While it's not completely perfect, we can still trace the rectangle boundary. It is, however, much better than a direct overlay for a very humble cost. So let us see the source code that produces this image editing example. So this is a rather short Python code. So I'm reading two images, the baseball and the football. I define the rectangle where we are working on. Then I'm building the system matrix A. I will expand it shortly. And then for each color channel, we build B, and we solve by the call LSMR the system A transposed AX equal A transposed B. And then I just save the image. And then in the system matrix, you can see that we have W by H unknowns. This is a number of pixels where our unknown is a pixel of our grayscale image. So W by H unknowns, and we have a number of equations that we impose on our unknowns. First of all, the perimeter of our image is W H H. So we have 2 times W plus H pixels on the boundary of our image. So we will prescribe the boundary conditions from the baseball photo, and then we sample the gradient for each pair of adjacent pixels. So we have 2 times W minus 1 times H minus 1 equation that we fill with the gradient, the finite differences. So the source code is really simple, and do play with the source code. Download it from the GitHub repo. Okay, so the takeaway message here is that thanks to their simplicity and their power, Laplace's and Poisson's problem are widely used in geometry and image processing, and it's very handy to know your friends. Let us move to the next example. I want to create a goofy portrait. Caricature, a type of exaggerated portrait, amplifies the characteristic traits of human faces. Typically, this task is left to artists, as it was proven difficult for automated methods. Here I show an extremely naive approach, starting with a 2D silhouette. This section is very closely related to Poisson image editing described in the previous example. Let us consider the following Python program. It defines a 2D silhouette that we can see in the bottom of the image as a closed polyline represented by 2 same-length arrays, x and y. The idea is to increase the curvature of the polyline, thus hoping to exaggerate the traits. To this end, we compute the curvatures via finite differences and store it in the arrays Cx and Cy. Then we want to solve the Poisson's equation with increased curvature as the right-hand side of the equation. So we perform a number of Gauss-Seidel iterations to solve the equation. Basically, this is the second-order finite differences for x that I want to be equal to the second-order finite differences of the input amplified by some quotient. Okay, at the bottom of the slide, we can see the evolution of the polyline. So this is the initialization, and after 10 iterations, the drawing looks very good. It's exactly what I had in mind. But what happens next? Well, there is no surprise. In the end, we obtain an inflated version of the input because it corresponds exactly to what we have asked for. To scale finite differences is the same thing as to scale the input signal. How to fix it? Well, we can stop the process after 10 iterations, thus exploiting the fact that a Gauss-Seidel has a slow convergence in low frequencies, but it is an unsatisfactory solution. It would be much better if the result was at the true minimum of our optimization routine. As before, let us rewrite the same problem as a minimization it will allow us to tweak the energy. The listing we have just saw corresponds to the following optimization problem to be solved independently for x and y coordinates. Here, xi are the input coordinates and x prime I are the unknowns. Recall that I highlight the unknown values in red. Quotient C corresponds to the scaling quotient, and the problem is separable in two coordinates, so I list here only the x part. Having rewritten the problem as a minimization, we can fix it. The simplest way to prevent the inflation of the model is to add a data attachment term. First, we start with the energy we have already written here, and then we add a second term. So basically, we want to scale the gradient, so we want to scale the gradient, and we want the deformation to be small. I want the output variables to be as close as possible to the input position. The quotients C0 and C1 allow us to tune the optimization to achieve the desired trade-off between the curvature exaggeration and the data attachment. To minimize this energy, we can solve the following system in the least square sense. As usual, you can find the source code in the GitHub repo, and this is what the code looks like. So basically, I have an array of x, I have an array of y's. I amplify independently on x and on y. And independently for these signals, I build a matrix A for n variables and 2n equations. So we have, for each point, we have an equation that that samples the finite difference, and we have an equation that attaches the variable to the input value. And this is what the result looks like. The sweet part here is that this formulation works out of the box for 3D surfaces as well. Let us look at the following Python program. So what we do, I load a triangulated mesh. So it's a triangulated mesh with a boundary. Basically, it's my face digitized because I don't want to mutilate other people. I build a system matrix A, and then for each coordinate x, y, and z, I solve independently here I solve a system A transposed A times x or y or z equal to A transposed B. So here B depends on the coordinate chosen, and A is a constant matrix for all coordinates. And having computed this least squares solution, I just store the result back in the mesh. The matrix A is built exactly as is shown on the top. So for each edge in our mesh, here I put for each half edge in our mesh, I sample. Here those are finite differences, so here I discretize also the gradient on the mesh. And then for each vertex of our mesh, I put a data attachment term Here I have decided to put a lighter data attachment term for the interior and a harder data attachment term for the boundary of the mesh. Well, I don't really know why. I could use the same quotient for the boundary as well for the interior vertices, but here I decided to do that. It's, by the way, it's a very interesting technique. It's a quadratic penalty. Basically, to move a boundary vertex here will cost, so this is 1/3, 30 times squared, it will cost 1,000 times more to move a boundary vertex than to move an interior vertex. Well, if we execute this source code, here is the result. On the left, we see the initialization, the boundary with a triangulated surface with a boundary, and we have exaggerated the traits by locally amplifying the curvature of our surface. So the takeaway message here is that reformulating as a least square problem allows for much easier tweaking. So we took a basic Poisson's equation, we have transformed it to a minimization problem, and we have just threw in a light data fitting term to the energy, and it allowed us to just do the trick. Okay, three more examples to go. Let us compute another deformation of the 3D surface. I want to cubify it. Well, I will mutilate myself to the max. The idea is to deform the surface by aligning triangles with one of the global coordinate planes, thus obtaining a Moai statue effect. First of all, for each triangle, we compute the coordinate axis closest to its normal, and I denote it as Aijk. So given a triangle with the normal vector Nijk, we test 3 coordinate vectors and take the one with the largest dot product. So basically we snap the normal to the closest coordinate axis. 3 different colors, blue, white and pink in the image, correspond to the axis. And then we want to deform the input surface according to this coloring, and it's really easy to do. My variables here are still the coordinates of the mesh vertices, and for the simplicity of notations, I call by Eij the vector corresponding to the edge ij in the input data, and E prime ij is the modified geometry, and recall that I highlight the unknowns in red. Here is a quick test. What would be the result of the following optimization? Take a few seconds. Well, without any doubt, you have recognized the Poisson's problem. So basically, we have asked for the output edges to be as close as possible to the input edges. And it's perfectly feasible in absence of other constraints, so our deformation is just an identity. Here you can see that writing E in terms of E and E prime is a sort of a differentiation with respect to our vertex coordinates. So we will add a few more terms to this energy to obtain the cubification, the desired effect. To do so, first we define the projection operator that takes a plane defined by its normal, and projects a vector to this plane. Then the desired geometry can be obtained by minimizing this energy. So how does it work? This part we have already seen. This is an attachment to the original geometry. And here, for each triangle ijk, we add a term that pulls the triangle to be aligned with the chosen coordinate plane. More specifically, for each edge of the triangle, we penalize its deviation. We penalize the deviation, for example, for the edge ij, we penalize the deviation of the output geometry from coplanarity with the plane defined by the axis ijk. Note the quotient C here, representing the trade-off between the flattening force and attachment to the old data. As always, the source code is available, and the takeaway message here is that again and again, with the same variables but different tweaking of the energy, we can obtain completely different results. So let us see the source code. It looks like this, a very short one. We load a triangulated mesh, in this case, as always, my face. This function allows it snaps an input normal vector n to one of the coordinate planes, and then independently for each coordinate, I solve three different systems: one system for x, one system for y, and one system for z. So I build a system matrix. We have one variable per vertex, since we are solving differently, separately for x, y, and z. And we have two equations per half edge. So for each half edge, let us return to the previous slide. For each half edge, I'm asking for it to be close to the original energy, and for each half edge, if necessary, I'm asking it to. It's not if it's not. Well, for each half edge, I am asking it to be coplanar with the coordinate plane that we have snapped the normal vector to. Okay, so here is the part that discretizes the gradient operator, and this is the part where I perform the snapping of the half edge to the coordinate planes. And you can see that my quotient C is equal to 2 here. Then I call the least squares solver and I store the data. Very simple. It is done. Okay, since we are going through examples, here we have 2 more examples to go. How to deform a character in a plausible manner? Well, usually this task is done by artists expertly rigging 3D models. However, simple deformation models can still produce satisfying deformations. So, starting from an input mesh, we choose a subset of its vertices, we move them, we lock them, and we want the rest of the mesh to deform accordingly. Here, both screenshots, before and after, are taken with the same camera angle, but the constraints imposed on the mesh naturally rotate the model around the vertical axis, while the tail moves to the other side of the character. Formally, we have the same choice of variables, namely the coordinates of mesh vertices, and our deformation will be controlled by a subset of vertices E, which will be forced to have the position pk. The first requirement why one might have is that the deformation must be smooth. So the very first idea to try is to preserve as best as possible the edges of the original surface while satisfying the position constraints. So recall that our unknowns are in red. We want the output data to be as close as possible to the input data while satisfying the positional constraints. Then the new vertex positions x prime can be solved by using the least squares problem, and once again this is a simple Poisson problem. The resulting deformation, however, does not look realistic at all. The surface is badly stretched near the constraints, and our deformation model is unable to create a nice global rotation induced by the constraints. How to make the deformation look like the character is moving? Well, humanoid motions are constrained by a skeleton, making any movement a composition of rotations around joints. To simulate this effect, we can ask for a deformation that locally resembles to a rotation. This way, the deformation will seem more rigid. To do so, we assign rotation matrices Ri to each vertex I, which will affect all incident edges. The least squares problem now has two sets of unknowns, the vertex positions and the rotations. And the energy tells us that for each edge ij, the modified geometry E prime ij must be as close as possible to a rotation of the input edge Eij. Here the cross denotes a multiplication of a 3 by 3 matrix Ri by a 3 by 1 matrix Eij. Note that this problem is a non-linear least squares problem, but in fact it can still be solved efficiently by alternatively solving for the vertex positions and solving for the rotations. If we fix the rotations, solving for the vertex position is a linear problem. It can be solved by 3 separate calls to a conjugate gradients algorithm, or even by Gauss-Seidel iterations. Finding the rotations is a so-called orthogonal Procrustes problem, which has a closed form solution. Let U sigma V transposed be the singular value decomposition of the 3 by 3 matrix built from the original geometry and a current approximation of the solution, and then we can set the rotation Ri to be equal U times V transposed. The resulting deformation is able to capture a global rotation of the model, while the position constraints nicely spread out across the surface. As always, a Python listing is available, we will see it very shortly, and you can find it in the GitHub repo. The takeaway message here is that, in fact, many nonlinear problems can be solved as a series of linear ones. And here comes the source code that allows us to deform the 3D mesh. So basically, I load a 3D mesh, I keep the original geometry. I define the vertices to be locked and their coordinates to be locked. Then I define a system matrix A here, and I perform a number of iterations where first I'm solving for the rotations and then I'm solving for the vertex positions. So I solve for the rotations here and I solve for the vertex positions here. You can see that solving for the vertex positions is done separately in 3 coordinates. So I solve one linear system per x, per y, and per z. Once again, the code is available. Do play with the code. And for our final example, I have chosen least squares conformal mapping, as it is one of the simplest problems that are not separable in dimensions. A mapping of the points of the surface to the texture, initially it was done for the texture mapping, is defined by a mapping function from a 3D space to a plane. And by inverting this function, we can colorize the surface using a flat image, for example, drawn by an artist. And the parameterization of a surface is a problem equivalent to flattening this surface. In our context, we are manipulating triangulated surfaces, and we define a parameterization as a piecewise linear function where the pieces are the triangles. Such functions are stored in texture coordinates, which are the 2D coordinates of the vertices of the triangulation. It's very difficult to define what a good parameterization is. There are many different ways to compare quality of maps. For instance, the distortion of a mapping can be defined with the Jacobian matrix. Ideally, it should be an isometric transformation, but this is an unreachable goal. In continuous settings, for example, there exist maps that preserve angles, conformal maps, and maps that preserve areas, orthogonal maps. In this example, we will manipulate discrete conformal or angle-preserving maps. Okay, so conformal maps. Here we see an example of the map. This is a map of the Earth, and you can see that it is an angle-preserving map. For instance, the meridians and the parallels are always meeting in a nice 90 degree angle. So conformal maps have a very interesting feature. Their distortion is locally reduced to a scaling. The stretching of the map is the same in all directions, and the map is called isotropic, which makes this type of parameterization relatively simple to manipulate. The conservation of angles implies that the texture locally is not elongated. On the other hand, the area is not conserved, implying eventually strong changes in stretching from one place to another on the surface. Computing such a mapping is a direct instantiation of the Cauchy-Riemann equations on a pair of real-valued functions of two variables, u of x and y and v of x and y, representing the texture coordinates. In this form, the equations correspond structurally to the condition that the Jacobian matrix is anti-symmetric. So basically, the Jacobian matrix has the form A, B minus B. Geometrically, such a matrix is always a composition of a rotation with a scaling, and in particular, it preserves angles. The Jacobian of a vector function uv takes infinitesimal line segments in the intersection of two curves in the parameter plane xy and rotates them to the corresponding segments in uv. Consequently, a function satisfying the Cauchy-Riemann equations with a non-zero derivative preserves the angle between curves in the plane. That is, the Cauchy-Riemann equations are the conditions for a function to be conformal. Of course, there will be no exact solution for a triangle mesh. Therefore, as usual, we can sum failure of this relationship to hold over all triangles. So we sample text coords at vertices of the mesh and interpolate linearly inside the triangles. It also means that the Jacobian matrix is constant per triangle. Note that there is a very handy formula to compute a gradient of a linear scalar function u sampled at 3 vertices of a triangle. With the help of this formula, we can write our objective. Function as follows. We want to compute a scalar function u and a scalar function v such that the gradient of u is equal to the gradient of v rotated by 90 degrees. Well, of course, we are not asking for the equality, but we minimize the deviation of the gradient of u from the gradient of v rotated by 90 degrees. Well, of course, we cannot do better than u equal to v equal to 0. It's a perfect solution. So beware of the zero solution, because such a map is unsatisfactory. As a quick hack, for example, we can pin 2 arbitrary vertices to some arbitrary places in the UV plane, and pinning one vertex determines the translation of the texture, whereas the other determines the rotation and the scale. This energy is very easy to minimize, and just as before, we need to solve just one linear system. And here is a source code that does just that. As usual, the code source is available in the GitHub repo. So we load the face to mutilate. Then I'm choosing arbitrarily two vertices to lock. I build the system A. So I build the energy with aid of our system A and the right-hand side B. And I call the least squares solver, and I store the results in the mesh. And our least square solver solves the system A transposed A x equal to A transposed B. Our matrix A has 2 times the number of vertices columns, because for each vertex we must compute a scalar u and a scalar v. This system is not separable in dimensions. We solve for u and v simultaneously. And then, as for the number of equations, first of all, we put one equation for each triangle. We put one equation for the gradient of u, and we put one equation for the gradient of v. And what does it mean plus 4? take a second. Well, of course, plus 4, it's just we have locked two vertices, and it means that we have locked u and v of one vertex and u and v of the second vertex, and it adds 4 more equations to our system to be solved in the least square sense. Well, this concludes our least squares through examples section. The main thing to recall here is that stating a problem as an optimization problem is a very powerful tool. Basically, we do not seek for an algorithm to compute a solution. We describe what a solution should look like, and then we let the solver to do all the job. Different variations of Laplace's and Poisson's problem are omnipresent, and you should learn to recognize them. Some problems are separable in dimensions, some are not. Some problems are linear, some are not. But a fair portion of non-linear problems can be linearized, as we will see very shortly. And finally, here goes our last section, entitled From Least Squares to Neural Networks. Nowadays, machine learning is a very trendy topic, and almost everyone wants to use it somehow, whether it's reasonable or not. Machine learning seems to be the answer to all the business prayers. It's amazing how people are now diving into the abyss of neural networks without ever looking back. However, it's even much more surprising to witness the existence of two irreconcilable camps: those for whom neural networks are the answer to the meaning of life, the universe, and everything, and those who despise neural networks and deny the right to use the tool. I do not advocate here for either party, and my 2 points are: first, neural networks are not the only machine learning tool. And second, there is no clear boundary between least squares methods and the neural networks. Okay, let us start with examples. The most simple, standard, and yet quite common machine learning problem is binary classification. Many very interesting and important problems can be reduced to it. For example, we can be given a set of data where n vectors are each marked with a red or green label. This is the simplest example, but in practice, a red-green data set can be really useful. For example, spam, not spam, email classification, where the input vectors encode various characteristics of the content, like the number of mentions of a certain magic carpet cleaning solution. And our goal is to build a function that takes a vector as an input and predicts its labels. First, we need to learn from the database. We need to build such a function whose predictions match the database labels. In the end, once the function is constructed, we can discard the database and use the function we have built as an oracle to predict labels for previously unseen vectors. Long story short, let's consider the simplest example. We have n real numbers and the corresponding colors that we encode as 0 red and 1 green. In other words, we have a sequence xi, yi as the input, where xi is a real number and yi is either 0 or 1. How do we build the classifying function? Let us start with the basics. We can fit a straight line to the set of input points xi, yi, thus performing an ordinary linear regression. Next, once we have the straight line, we can endow it with the classification rule. If yi is superior to to 1/2, then the X is green, otherwise it is red. The bottom image provides an example. The colored dots show the database, and the straight line is the linear regression result, and the decision boundary is here, is shown by the dashed line. All points on the right of the line are classified as the green and on the left as red. We can see that the database is perfectly learned, there is no misclassification, and for the sake of simplicity, I do not make the distinction between the database we learn on and the database we use to assess the quality of the classifying function. So this classification was done by this code. It's a really simple one. So we have the samples. Half of the samples are red, half of the samples are green. We build the matrix for the system, and as usual we solve the problem A transposed A times X equal A transposed B. It may sound stupid, but ordinary linear regression is not always a bad choice for a binary classification. Of course, it only works if certain assumptions about the input data are satisfied, like independent and normally distributed class samples. If, however, these assumptions are not met, we may face problems. In this example, I have added to the previous database few more green samples. This affects the linear regression, and we encounter misclassification in the database entries, even if the database is perfectly separable. We can fix this situation by fitting a nonlinear model. And to do so, let us first meet the logistic growth model before we return to the classification. Okay, logistic growth functions are useful as models accounting for constraints placed on the growth. An example is a bacteria culture allowed to grow under initially ideal conditions, followed by less favorable conditions that inhibit growth. Imagine a colony of bacteria that is growing in a petri dish. Then we can model the area A, say in square centimeters, as a function of t, and t is elapsed time in hours. Here C is the carrying capacity, W0 is the initial population size, and W is the growth rate. Let us say that we want to recover the parameters of the model from an experiment. We have a series of n measurements, AI, Ti, as shown in the scatter plot. As usual, I highlight in red the unknown values. Under the assumption of independent and normally distributed errors with zero expectation and common variance, maximizing the likelihood for the general nonlinear model is equivalent to minimization of the sum of squared errors. So, as I said, red is unknown, so we are looking for an unknown function a of t. The shape of the function is known, but we want to recover its parameters. There are multiple ways to deal with non-linearities of a model, and for example, we can try to apply some transformation to the model itself prior the fitting, and let us try it. So we have this logistic growth model. We can simply rewrite it as follows, and to apply the logarithm to the both parts. So basically, this is an equivalent transformation of the model. If we have an estimation for the parameter c, this model is well suited for an ordinary linear regression. we can find the estimation of parameters by solving the following system in the least square sense. So how can we estimate C? Well, knowing that it corresponds to the carrying capacity, we can do a quick and dirty estimation by putting C to the maximum of all our measurements AT plus a small constant epsilon to avoid a division by zero in our model. So this can be done by the following code. We have the elapsed time, we have the area size for the bacteria growth, we evaluate the C very dirtily, and then we solve a simple linear regression to fit our parameters. And here is the logistic curve fitted to our data. Of course, the fitting is far from being ideal. We have estimated the distance from the points AI to the curve A of TI in a very indirect and distorting way. Nevertheless, this fitting can be of use as a first guess for further optimization. There are other ways to deal with the non-linearities. For example, we can linearize our objective function. And to do so, let us denote by R the residual vector between the input labels and the prediction. Then our problem can be rewritten as a minimization of the squared norm of the residual vector. And it can be solved by, for example, the Gauss-Newton algorithm. The idea is extremely simple, starting from an initial guess B, for example, the one that we have built by an ordinary least square regression of the transformed model, or even just with 3 random values. We build a sequence of approximations by adding at each step an increment. And to find the increment, recall that green is known, red is unknown. And to find the increment, we can linearize the function R at the point bk. So this is a first order Taylor expansion. And here J is the n by 3 Jacobian matrix evaluated at point bk. Then we are looking for such an increment delta that is the squared norm of the residual is minimized. This again is an ordinary least squares problem equivalent to solving a 3 by 3 system of linear equations. So basically we want to solve the system J times delta is equal to R in the least square sense. So we are solving the 3 by 3 system J transposed J delta equal to J transposed R. And here is the logistic curve fit to our data by solving a series of least squares problems. So this is the code that allowed us to do this. We have the samples. We perform 5 Gauss-Newton iterations. We build the system matrix J. We build the right-hand side R, and we solve an ordinary linear least squares at each iteration. Okay, back to our classification example. Fitting a sigmoid shows a clear advantage over ordinary linear regression classifier. So this is our linear regression classifier that misclassifies some elements in our learning database, even if it's perfectly separable. So we had an idea to fit a sigmoid, and we leave the same decision rule if y of x is superior to a half, then x is green and red otherwise. and thus we have two parameters only, w and w0, and we can resolve them by solving the optimization problem using a Gauss-Newton algorithm. So in this example, the training sets are linearly separable. There is a, and thus we did not have any misclassification in the training set by fitting the sigmoid. There is one caveat though. It might seem that linear separability is a good news for binary classification. But for instance, in this example, the decision boundary is given by a t such that 1/2 is equal to 1/1 plus exponent of minus wt minus w0. And by solving the system, it's pretty simple to see that t is equal to w0 divided by w. The decision boundary would not move a tiny bit if we multiply both w0 and w by a constant superior to 1. The boundary doesn't move, however, the scale does impact the likelihood in the logistic regression by causing the logistic function to become more and more steep. If we have found such a decision boundary that all the samples from the learning database are correctly classified, we can infinitely scale the weights w and w0, pushing the predictions closer and closer to their correct labels. And thus the logistic growth function converges to a Heaviside function, so it's a step function. And it's one of the numerous possible instances of what is called overfitting. The model is becoming overconfident about the data and uses very large weights to describe it. There is a very simple solution to this problem. We can, for example, regularize the weights. The most basic regularization is to add a simple term to our energy that penalizes large weights. It turns out that we have just built and trained a neural network made of a single neuron. One neuron perceptron with mean squared error loss function is completely equivalent to our nonlinear least squares problem. While the example that we have shown here is unidimensional, it is straightforward to generalize it. We can fit m-dimensional logistic function 1/1 plus exponent w transposed x, where w is m plus 1 parameter vector with the last element of x is the constant 1. And w transposed x is the corresponding linear combination. Note that the decision boundary is always linear if it's a point in 1D, a straight line in 2D, a plane in 3D, and so forth. And figure on the right shows the energy plot for the unidimensional example. Note that I have added a regularization here, so I want the weights to be as small as possible. While the function has a unique minimum, it is a highly non-convex function, thus making numerical optimization a non-trivial problem. Turns out that for this particular case, we can make the function convex. Just an example, we can use another loss function. We have used least squares function, And we can use, for example, cross-entropy loss function. So logistic regression is another technique borrowed by machine learning from the field of statistics. As before, the basic idea of logistic regression consists in that the space of initial values can be divided by a linear boundary, a straight line, into two areas corresponding to classes. Simply answering red or green is pretty crude, especially if there is no perfect rule. Something that takes a noise into account and does not just give a binary answer will often be useful. In short, we want probabilities, which means that we need to fit a stochastic model. Well, let two possible classes encoded by y either 0 or 1, and assume that the probability of the class to being equal to 1 having the point to predict a label on x and having learned the parameters be the same logistic function. And here again, w is m plus 1 parameter vector with last element of x is a constant 1. Here we interpret this sigmoid as a conditional distribution of the response y given the input variables. Up to this moment, there are absolutely no changes with respect to the previous section. We use the same one neuron perceptron. The crucial difference comes from the way we will train it. In the previous example, we have minimized the mean squared error loss function, implicitly assuming presence of zero mean Gaussian noise in the labels of the dataset. Our data, however, is not real valued but binary valued, and thus Bernoulli's scheme is most suited for this situation. Exactly like we have made it in the first section, we can write a log likelihood as follows. And to fit the sigmoid to the data, we need to maximize the log likelihood. All hard decisions are already made, so it's time for basic calculus. To maximize the log likelihood, we set its derivative to 0 and obtain m plus 1 nonlinear equation in W. Refer to the course notes for the full details of the derivation. We can solve this system in an iterative manner using Newton-Raphson steps, and it turns out that the Hessian matrix is a positive definite. So our energy is a very nice and well, it's convex. Okay, here is an example of cross entropy loss function being learned on a 2D database. Refer to the GitHub repo for the source code that produces this image. And basically it looks like this. We have a 2D database with corresponding colors. And then we perform 5 iterations, Newton-Raphson iterations, and in fact we are performing iteratively reweighted least squares. So we build the Hessian matrix and we solve ordinary least squares for each step. Okay, now we have mastered the art of binary classification with linear decision boundaries. What about nonlinear boundaries? A straightforward way to do is plug something nonlinear, for example a polynomial, instead of W transpose X. For example, here we can separate the sets by using a quadratic function, so we can plug a quadratic form here instead. It has already been done. However, the problem is that such a prior, the shape of the separating function, is hard to put on the data. However, the optimization scheme is it's hard to put the prior on the data, and the optimization scheme is different for every choice of this separating function. Here, neural networks come very handy. So, for a linear decision boundary, we have trained the simplest possible network built from a single perceptron that I show here. Our last example in this section is a regular perceptron made of 3 neurons. 2 neurons in the hidden layer and 1 output neuron. You can see the topology. The input is the same as in the previous example. We have a series xi, yi as the input, where xi is a real number or a vector, m-dimensional vector, and yi is a binary number. It's either 0 or 1. The loss function E is parameterized by 3 m+1 component vectors, u, v, and w. So we need to find u, v, and w to do all the linear combinations. The gradient of the loss function with respect to each weight can be calculated using the chain rule, and computing gradient one layer at a time, iterating backward from the last layer to avoid redundant calculations of intermediate terms in the chain rule. This is an example of dynamic programming. So basically, I train this 3 neurons neural network by this piece of code. I have the samples. This is the function. Is a logistic function. I have 9 unknown values. I start with 9 random values, and then I perform a number of gradient descent steps. So I compute the energy, and I perform the gradient descent, where alpha is the learning rate. So let us deconstruct the network to understand how the nonlinearity of the boundary can be obtained. A perceptron with a hidden layer, so we have 3 neurons. The perceptrons from the hidden layer combine sigmoids, and then we apply a sigmoid over it. In our example, the data is 2-dimensional, so for the sake of simplicity, imagine that the hidden layer neurons produce unit steps instead of sigmoids. So we have a unit step that is 0 here and 1 here. And then we have, for example, it's output of this neuron. And then the output of this neuron is another unit step, for example, 0 here, and 1 here. If our weights W0 and W1 are 1 and W2 is 0, we obtain a function that is equal to 0 here, 1 here, 1 here, and 2 here. So basically, we can isolate a quadrant. So here is the result of the code that I have shown you earlier. Once again, refer to the GitHub repo for the full source code. So we can choose the type of the decision boundary by adapting the topology of the network. But be aware that you are entering the black magic realm. Generally speaking, there is no whatsoever guarantee of convergence. And even in this simplest network, we have too much degrees of freedom in our training dataset. For example, we can negate all weights without affecting the decision boundary. As I have already said, it's surprising to witness the existence of two fighting religions. Neural networks is a gift of God versus neural networks is a no-no. Obviously, we cannot fit all the data with a straight line, but with powerful feature extractors, we may be able to reduce our problem to a much simpler one. To put it into perspective, this is what neural networks do effectively. The only difference being that we use some non-linearity as the activation function in the first layer. If we remove it, we could look at the first layer of the neural network as a least squares problem. I mean fitting a plane on the data, activations from the previous layer. This concludes my presentation, and obviously it's not possible to master even the few examples that I have provided from the presentation alone. Even if you have paid a full attention, the presentation is way too rapid in most aspects. This is why we give you the source code to play with, read the course notes, check the source code, modify the source code, and most important, have fun.